have some sort of a take-home final exam next Sunday. That's the plan. So now let me. I did get one request over email from Gopinath Sundarajan. But before I get to that, any other questions, comments? So the assignments are all marked almost, except for the last two, and that we hopefully in the next few days we will submit them all. Any questions, comments? So Gopinath wanted to know about graph isomorphism. I will let me get on to it unless somebody else has any other question to me.
Good evening, sir.
Yeah.
Actually, the way you taught in, you said that start with some simple problems and then discuss the time complexity like sorting n square, then go to n log n, it's like that, and start with some matrix multiplication, simple problem, then go with next. So I have one question regarding that, regarding GCD. I have done something that in first half, I do something simple that uh, if you find the GCD of two numbers, then and that number A and B, then first that list the divisor of A and divisor of B, and then compare and then find the largest common one.
Yes.
Okay. That is that I got some time complexity that okay, and then start with next is that Euclid algorithm.
Mm-hmm.
Then can you just little bit elaborate about that, how Euclid algorithm complexity is going on?
Yeah, I don't remember exactly, but let's look at the simple algorithm you said, right?
Yes, yes.
What is its complexity? So I want to find GCD of some A and B. So your algorithm is
Find the divisor of A,
list
all divisor of A,
all divisors of A
all divisor of B.
and then list all divisors of B and pick the common max.
Common maximum, all largest.
Max, yeah. What is the complexity of this?
Complexity means I thought that you said that in prime numbers algorithm that we up to go up to root n. So I thought about that in this algorithm also we can go up to root n also, or individual divisor.
Okay, go up to root n, because then you know that root A basically A
Root
by whatever A by X will also be a divisor. So you get two
divisor. Yes.
you get two divisors at every point of time. Once you divide, you get the common. Yeah. So it will be like order square root of A plus square root of B.
B.
This will be the complexity of this algorithm.
Yes.
Okay. However, in
here actually we are taking the total number of divisions.
correct, exactly,
Yes.
right.
Yes.
But in Euclid's algorithm, how do you do, right? Yes, maybe that's Yes, that's better. So in Euclid's algorithm, what it does is, suppose A is bigger than B, then you,
Taking the remainder actually.
right. So you look at A mod B.
Mod B, yeah.
So you look at A, so it will be GCD of A and A mod B. So your first step would be to,
Find the first remainder.
yeah, so take A and divide by B and then you get the remainder, right?
Mm, mm.
So what happens now, your number has become much smaller than B.
Mm.
Um, okay, how does the algorithm work? So I take, uh, let's say let's do it. GCD of 75 and
Some example that will be
12.
very
Okay.
useful.
Then this is equal to, what do you do? It's basically take 75, divide by 12, that's
12.
2. So 3, that's basically 3 and 12.
Mm. Then again taking remainder of 3 and 12.
Right. Then you're done. So
Uh,
this will be like 3.
3.
Yeah. And look at how fast we are finding this, right? Algorithm is done pretty much. So the answer is 3. Without going through all the devices of 75 and so on. So this algorithm has a complexity of log A plus log B.
Yes.
Okay, I just don't exactly remember how it
Mm.
is.
But the base is something different.
Basis doesn't matter, right?
Okay.
Yeah. Yamini, do you remember how it is? Or have you seen this?
I just know the procedure of GCD, but I don't know how the time
Complexity.
complexity is, sir.
Yeah. So it turns out to be it's log A. I mean, this is one of the first algorithm, you can say, the first algorithm. And the complexity is log A plus log B because simply um, you quickly converge, your numbers become much smaller and smaller very quickly.
Is it working like, means similar to working like that the binary search is like that?
Not really.
But means the way it's decreasing,
Yeah. See, the worst case would be sort of like this Fibonacci number. So if I have basically your,
some consecutive Fibonacci number, if I give the input,
yeah,
then
yeah. If
okay.
I give the consecutive, let's say some Fi and Fj or Fk plus 1 and Fk, you're going to subtract. So let's for example, this would be the hard case. If I want to do GCD of k plus 1 and Fk, what do? This is equal to GCD of, you subtract out there is no common factor, so you subtract out Fk and the remainder would be Fk minus 1. So it will be Fk minus 1 comma Fk. And then when you subtract out, this would be GCD of Fk minus 2, Fk minus 1, and so on and so forth. This
Okay.
would be sort of the worst case. So the number of steps you need will be something like k steps.
Case steps now.
Okay?
Okay, okay.
But the number, the kth Fibonacci number, or k plus first Fibonacci number, is some exponential in k.
Okay. Okay.
The actual value of, if you know how the Fibonacci numbers grow,
Mm.
the kth Fibonacci number is exponential. It is where phi
Yes,
is
yes,
1
yes.
plus square root of 5 by 2, roughly. Okay. So for such an exponential number, you are getting it in k, which means this k is logarithmic in f of k. So
Okay.
K is basically order log f of k, because f of k grows exponentially in k. So this would be sort of like the worst case, where you are looking at these consecutive numbers where there is no division happening. Then uh, somehow this is how you argue that in logarithmic time you will reach. But the point is, yeah, you're right. I mean, the main message you picked up about starting with simple algorithm and then getting to more complicated algorithm. That's a good point.
Yes, yes, yes.
Simple algorithm, you first realize that it takes something like order square root of a plus square root of b. And Euclid's algorithm, I'm pushing the details. I need to think about why it is log a plus log b, but that's essentially the worst case happens something like this. Yeah. So, I mean, one other example I have always seen, for example, um, you said you are doing PhD, right, Santu?
Yes, 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 sir.
So you're not actually done an algorithms course, or this is your
Actually, I have done algorithm course long time ago,
okay,
15 years ago.
okay. So, for example, this is another closest point among some n 2D points. Okay, I have given you some n 2D points like this. That's your input. And the question asks for what is the closest, the pair that has the smallest distance. Okay. Now, this is a standard divide and conquer example in most algorithms course, where you split it into arrange it in increasing, sort it first, and then divide it in two parts, find the closest pair on the left, closest pair on the right, and then do some other things to get divide and conquer recurrence, 2 by 2 plus order n, and get an n log n.
You have discussed that in the
Okay.
video.
But now if I ask you, give me an n square algorithm for this. I know many students and teachers really struggle.
N square,
Can you give me an n square algorithm?
we have to choose 2 point
Yeah,
among the endpoints. Then take every 2 points distance.
exactly. That's it, right? Pick every pair, find the distance. Finding the distance is constant time. That's Euclidean distance.
Yes, yes,
And do it for every pair. There are n choose two pairs and find the smallest.
yes.
It's n square. So somehow my recommendation always is do this algorithm first. Make it explain the n square, and then they'll be able to appreciate the n log n algorithm. N log n algorithm is so involved. You
Hmm.
do it in over 2 lectures. But if I ask for n square algorithm, they just blank out. So yes, I'm glad you picked up this main message of any problem. Start with some simple algorithms, then you'll be able to appreciate the more complicated algorithms.
Thank you, sir.
Yeah. Okay. Okay. Any other questions or comments before I talk about graph isomorphism, which is what Gopinath wanted? Yeah. Okay. So in general, isomorphism means, two objects are isomorphic means they are the same. That's what it is, right? You can talk about group isomorphism. You can talk about various things. So, for example, if I ask you, are these two graphs isomorphic? Are they same? Right? Pictorially, if you see, they look different. But for us, graph is an abstract object. It is, these edges don't mean anything. I could have drawn like a curve, right? So I could have, for example, I could have just drawn All I know is A and B together, the pair forms an edge. C and D forms an edge. A and D form an edge. B and C form an edge. So graph means you have a set of vertices and a collection of pairs of vertices which are edges. So now if I ask, are these two graphs the same? Are they same? Yeah.
Yes,
Yes,
yes.
yes.
They are the same, right? Even though I have drawn pictorially, they have four vertices, four edges. That's not the only reason they are the same. See, four vertices, four edges, they cannot always be the same. So, for example, this graph, these two are not the same. Even though they have four vertices and four edges, these two graphs are not the same, but somehow these two are the same. How do you formally define they are the same?
There is some mapping between two.
Exactly. That's what graph isomorphism. So if I write this as 1, 2, 3, 4, then there is a mapping which makes these two same. That is, I can map A to 1. And where do I map B to?
3.
3, yeah. Or 4, for example. Certainly not 2. Why not 2?
2 is not adjacent to.
Because A and B are adjacent, 1 and 2 are not adjacent. So B gets mapped to maybe 3. Then I know C should get mapped to 2 and D gets mapped to 4. So if you look at this mapping establishes that these two graphs are same, because whenever you have an edge, for example, AB is an edge, then if you look at the mapping f of A, f of B, which is 1, 3, that's an edge. And whenever there is no edge, A, C is not an edge, and 1, 2, which is the image of this mapping, is not an edge. So that's it. So what is the graph isomorphism question? I give you graph G1 and G2. Are they isomorphic? So one simple sanity check is that they certainly both should have the same number of vertices and same number of edges. But clearly that's not enough. So then this question asks, is there a mapping where I can map the first graph vertices to second graph vertices so that edges are preserved? Now clearly there is a simple n factorial algorithm, right? So this has some n vertices, and this has some n vertices. So there's a clear, simple n factorial algorithm where you take the first vertex, map it to some arbitrary vertex, and then take the second vertex, map it to some other arbitrary vertex, and so on and so forth. And you will check whether they preserve edges. If not, try a different mapping, and you can run through all mapping. Now, interestingly, the polynomial, is there a polynomial time algorithm is a very, very famous open problem. It's not resolved yet. In fact, it's not even known whether it's NP complete. People believe it has a polynomial time algorithm. There are very good algorithms, not necessarily polynomial time, but something like n power log n kind of algorithms exist. But this polynomial time algorithm is open, and we don't know whether the problem is NP complete. People believe it is not NP complete. It is actually polynomial time solvable. But your problem sheet or somewhere, I am asking some version of this to show NP complete. Do you remember what that problem was? Not quite.
Subgraph isomorphism, sir.
Subgraph isomorphism. That is different. Okay. Graph isomorphism is open. We don't know. Subgraph isomorphism is you are given G1 and G2. This is the input. And ask, is G1 isomorphic to a subgraph of G2? Okay, so we already discussed isomorphic means it's the same. Okay, so then this question is asking, here is my G1. Is there some subgraph here which looks isomorphic to G1? So is there a copy of G1 inside G2? Okay, you can think of it as, is there a copy of G1 inside G2? That's the question. Okay, how do you show it as NP complete?
Checking the edge between these two graphs.
No. How do you show any problem NP complete?
I didn't get you. Can you repeat?
How do you show any problem NP complete?
I have to reduce to already known NP complete problem.
Reduce from a known.
From.
Okay, you said NP complete.
You have to show first it is an NP.
NP, that's
then
right.
you have to reduce from a known NP.
Yeah.
Or NP complete.
That I have to prove NP hard.
Okay. So first, how do you show it is an NP? Well, suppose the answer is yes. How do you verify it?
We have to check edge.
I mean,
G1.
What is the proof you will give? First of all, to show NP, you have to give a proof for the S answer, and then the proof has to be verifiable in polynomial time. So what is the proof?
The mapping.
Mapping and the copy of G1. Yes.
Copy of G1.
The subset of vertices of G2. You have to give that subset of vertices of G2 and a mapping from G1 to our vertex set of G1 to that copy you are establishing. Check. So that's a proof. The subset and the mapping. And you verify, whether the edges are preserved and so on. So that's the NP, right? So proof is a subset of vertices of G2 and a mapping subset, let's say S, and a mapping from the vertex set of G1 to S. Always when you say NP, this is, you have to give a proof or a certificate, and the verification algorithm verify that G1 and S are isomorphic. More precisely, the induced subgraph on S by checking adjacencies. Yeah. Okay, so this is the easy part. We're trying to show NP. Now, how do you show NP hard? You have to reduce from a known NP hard problem to this problem. So what problem do you reduce from? Have you seen any other problem NP complete which looks for a copy of something in a graph?
Click.
Independent set, Hamiltonian cycle. These are all looking for some structure in a graph. So you start with the click problem where you are given a graph and I want to know whether there is a k-sized click in the graph, right? G and K, and you are asked whether there is a k-sized clique. Now, translate that into a graph G and create your clique G2 or G1. G2 will be the original graph and G1 will be the clique, K clique. So now, is there a K clique in the graph? Is same as asking, is K clique isomorphic to a subgraph of G? It's simple enough. So, Gopinath, is the isomorphism concept clear? Is that does that answer?
Yes, sir. Yes, sir. Thank you, sir. The brute force method of determining whether two graphs are isomorphic,
Yeah. Okay.
that is n factorial.
Right.
So what I understand, sir, suppose I'm given adjacency list of two graphs.
Mm-hmm.
I take the first vertex of the first graph,
Yeah.
compare with the entire list of the second graph. If there is a match, yeah, I am done. Then I go one by one by one and I get n factorial.
No, that's not enough. I mean, what do you mean by you are done? If the two lists match, see, remember, that's not enough, right? So, see, your first list will say I am adjacent to vertex number 2, 7, 12, and 15. Okay.
Yes.
In this graph, there may be some A which may be adjacent to some B, D, E, H. Now, you can't conclude anything by looking at these two lists because you don't know what this B corresponds to. B. So, if you have 2, 7, 12, 15
Correct.
here, you don't know whether B corresponds to 2 or 7 or 12 or 15. What you have to do this mapping.
First, I have to do vertex mapping.
Yeah. So, if you are asking what is that n factorial algorithm, all I will do is, so let's say my vertex set is V1, V2, Vn, and let's call this vertex set as U1, U2, Un. Okay. This is my graph G1, this is my graph G2. Then what do? I map V1 to U1 arbitrarily. Right? I have to map. I'm going to test it, try whether this mapping works. Then I take V2 to U3, something arbitrarily. Then V3 to U2, V4 to U5, something. So I do this mapping and then check whether adjacencies are preserved.
Okay.
If yes, then good, I've got a mapping. If not, I change the mapping.
Okay.
So the question is simply how many mappings are there, right? So I have V1 to Vn and I have U1 to Un. How many different mappings are there between these two vertices? Bijective mappings, right?
Yeah. Okay.
Well, so V1 has like n choices. Once I fix that n choice, then V2 has the remaining n minus
n
1.
minus 1 choices.
V3 has the remaining n minus 2 and so on and so forth. So that will be the n factorial choices.
Okay.
Because it has to be bijection.
Okay.
So that's the n factorial algorithm. I don't even look at the adjacency list and so on because that I don't know. After I fix the mapping, I go and check the adjacencies and see whether this mapping works. Because once you have the mapping, then you look at the appropriate adjacency list and check whether they are okay.
Okay, sir.
Right?
So in fact, multiplication factor of this complexity will be much more higher.
You mean after the n factorial?
Ah,
Oh, after the n factorial, you run through every edge.
every edge.
Every edge to see whether whenever you have an ij edge, fi, fj should be an edge. That's all.
Okay.
And vice versa, both ways. Yeah.
Fine, sir.
Yeah. This is a very simple graph isomorphism algorithm, but there are, this is a very, very well studied. There are lots of papers written on it. In fact, my own colleague Arvind at IMSC has spent a lot of time looking at graph isomorphism of a lot of special classes of graphs where it's all settled. The general problem is very close to getting settled, but it's still open for quite some time. Whether it's polynomial time solvable or not. Yeah. But subgraph isomorphism is NP complete.
Ah,
Okay. Any other questions, comments?
sir, even the graph isomorphism,
Yeah.
it is in NP because once it
It
is
is an
given,
NP. Sure. Yeah.
it
Yeah.
is in NP, sure.
Yeah. Yeah.
But what makes it is not NP complete, sir? We could not able to find any other hard problem
To reduce
uh,
from. Yeah.
to reduce them. Mhm.
Yes. Also, there are pretty efficient algorithms known. I mean, we don't have a n power. So right now, something like n power log n or some
Okay,
kind of algorithms known. We want the exponent to be a constant. We don't know that, and
okay.
typically NP complete problems do not have such a nice algorithm.
Ah, yes, sir.
So that is also another reason people don't believe it will be NP complete. It's
Okay,
actually close to polynomial time. But you're right, it is an NP easily. And um, in fact, 20, 30 years ago, there were two. In fact, primality was another problem which is open for quite some time.
yes, sir.
I think I mentioned it in my videos or somewhere else.
Yeah,
That, by the way, there even NP is not easy,
okay.
right? How do, if I have to tell you that a number is prime,
Ah,
to tell you a number is composite is easy.
is easy.
To give a proof and the easy verification is easy because you just have to give a factor. To show a number is prime, how do I even convince? It's not easy, but there was an NP proof known using some number theoretic algorithms, number theoretic lemmas and properties. The first time it was shown it is an NP. And then there was a randomized polynomial time algorithm known. And then people came up with the polynomial time algorithm. And this was the group from IIT Kanpur. About 20 years ago, they proved the first polynomial time algorithm for primality. Another problem which had a very similar history is linear programming. This was another problem. It was open and it had an Indian connection again. Narendra Karmarkar came up with the polynomial time algorithm, and there was also a Russian algorithm, Kachayan's algorithm. So, graph isomorphism in that sense is waiting for a breakthrough. A polynomial time algorithm can happen anytime. So,
Good. Thank you, sir.
I submitted assignment 4, 5, and 6, but it is showing not submitted.
sorry, you have not submitted.
I have submitted assignment 4, 5, and 6 also, but it
Okay.
is showing not submitted.
Oh, can you send an
I
email?
submitted all assignments, but it is showing first 3 only submitted.
Sir,
Yeah,
I have received it.
you have received it.
Prasad sir, assignment 4 is being received. I have to check for 5 and 6, sir, whether
Okay.
it is received or not.
Yeah, if there are any questions, please send an email. No problem. Send it to me or to Yamini. Also to the NPTEL team, they can resolve it. Yeah. Okay, if there are no more questions, I'll see you next week. Please do come prepared with questions because Sunday we will have the exam. It will be like a take-home exam. They will release it in the morning around 10 o'clock, and you have to submit by evening 5 o'clock or something like that.
Sir, is
And
it open book, sir?
it is open book, but I mean, once I release it and you do it, I have no control on. It's not closed. We don't have a monitoring mechanism. But as usual, we say if you refer to anything, please acknowledge it. And this will be short question answers. So yeah.
Okay.
Sir, what about the Viva? Like you mentioned, it will.
Yes, yes. Thanks for reminding that. So what I will do, that's very important. Maybe I will send an email making an announcement that for some selected people, I will have a Viva after the test, because essentially to make sure it is your own answer or to help understand. I mean, it's hard to do a Viva for everybody. There are about 100 participants. I don't know how many will turn up. The number is small. I'll try and do it for everybody. Otherwise, for a selected number of people, I will have a Viva before finalizing the grades. So you will be sent an email fixing a time for and asking for convenient time for a Viva, hopefully in a week after the final exam.
Okay, sir. Thank you, sir.
Okay. Yeah, Yamini, you have any comments? I mean, you have any thoughts on how we can do this Viva scheduling?
As you said, we can ask them the convenient time and fix up, sir.
Right.
And it cannot be conducted for everyone. Maybe
Right.
a selected set of
Right.
students.
After we evaluate the tests,
Yes, sir.
we will shortlist and then send an email. Yeah.
Yes, sir.
Right. Hopefully in a week after that. Yeah. Okay. Thank you very much. I'll see you next week then. Good night.
Sir, thank you.
Yeah.
I just last question.
Sure, sure, sure.
If you just let me know that, what are those topics? You already have said that in lecture many times, but still I am asking that what are those topics I should concentrate more on this?
For what?
For total data structure and algorithm.
Yeah. I mean,
Means
when you
every
say,
data structure and every algorithm are not that important, but something that are very very important that uh, are like we can use that and well, from learn that from that data structure
okay.
algorithm
So,
can apply.
right. Okay. So let me tell you about data structures to start with. So the actual implementations of the algorithm, whether you are doing insertions, deletions, the different case analysis, all that are hard and you can't remember and they are not important. But what is important is we have looked at about 3 or 4 essential data structures, right? Balanced binary search trees, heaps, and maybe a bit of suffix trees. All I want you to know is which data structure is used for what. What are the pros and cons of the data structure? So what can you do in a heap which you cannot do in an AVL tree? What can you do in an AVL tree which you cannot do in a heap? So when do you apply balanced binary search trees? For what kind of operations? This is the high level understanding you should have, because this is what is required in real world. How do you insert into a heap? How do you insert into an AVL tree? Those are messy details. I would not say anything is not important. Everything is important, but in a relative sense, more important thing is what data structure to use for what operation, and which in each of these data structures, what is doable, what is not doable efficiently. This is the kind of understanding you need. And similarly, when it comes to algorithms, somewhat similar. Yes, at a high level, what are the complexities of these algorithms? Um, what are the uses of, so for example, BFS, DFS? We have seen those kind of things. Where are they used? What is the point of them? Those are important. And we represent a graph in an adjacency matrix or adjacency list. What are the differences? When do we use adjacency list? When do we use adjacency matrix? Those are important in the sense that to efficiently implement some algorithms, should I use adjacency matrix, adjacency list? What are the differences? That's important. And then this whole notion of NP completeness, of course. It's very hard to remember any particular NP complete reduction, but the general concepts are important. What do they mean? what does NP mean, what kind of problems are, NP complete means what can you say, anything about a problem if it's NP, if it's an NP complete, that kind of things are important.
Thank you, sir.
Yeah. Okay, good. Thank you. I'll see you next week then. Yeah.
Thank you, sir.
Bye for now.